I hope everything is visible, but I'll zoom in or I'll go into presentation mode. Uh, F5, right? Never mind, I don't know how to do it. Language-driven semantic segmentation. Let's start out by understanding what the motivation behind this paper was, or what the paper was trying to do. So, semantic segmentation aims at partitioning an image into coherent regions with their respective semantic class labels. So, I'm pretty sure every one of you have gone through the reading group or the research paper, and that classic or that striking image in which you saw that the image was able to classify a given or the model was able to classify a given image into multiple regions, describing this is the cat, or this is the pet, or this is the vehicle, and with such high accuracy was basically the purpose of what LSEG is planning to do. But the thing is that this has already been done before, and it's nothing new in this scenario, because you might have already seen that it's common footage where basically you see footage and you see captions and you see a square bracket around a particular entity, and a particular confidence score with saying what entity it is and how much confident it is. But what LSEC provides in advantages are something we're going to be learning earlier. So one of the disadvantages of these previously mentioned models, such as CLIP, was that they were using few shot or many shot approaches. Now, what is few shot or one shot or many shot approaches? So essentially, if you're working with few labels, or working with a little bit of your data as labeled, or one, or just even one annotated piece of data, that means you're working with annotated or labeled data. In the case of image segmentation, that might not seem like a big deal, but the problem comes in the fact that image consists of thousands and thousands of pixels, and each one of these pixels has to be manually annotated and has to be separated into different regions as per what entity is depicting. So for even one image, that could consist of up to 10,000, 20,000 pixels in itself, and that becomes very tedious for human annotators to work on. So and that's why few shot and one shot approaches were implemented, because in these scenarios what would happen is basically you would take one or two, you would basically label or annotate one or two images, and that would be it. Your model would be able to build upon that without using any more data. Just using those one or two images, you're able to move forward with that. And but even within few shot and one shot approaches, the problem is that even these images, what they try to do within these images is that they try to fit as much relevant data into one or two of these images, so that the model is able to train efficiently. But even in that process, it is very laborious and time consuming. So LSEG is one of the approaches which uses zero shot approaches, which bypasses all of that. And how it does that, because you're basically creating a model, a classification model, without using any labeled data. And how it does that is something which is very interesting, and we're going to be learning now. So this is what I was talking about. Zero shot, few shot are semantic segmentation approaches, which will basically require some labeled data. And but LSEG, how is LSEG able to overcome that? We'll be learning that now. So the inspiration for this model, as you probably know, is the CLIP model for image classification. And ideally, or what the point or what the summary of the approach is, that it uses two separate models, which is one of which is a text encoder, and the other one which is a image encoder or an image embedder. So both of these, what they do is basically embed the meaning of the two inputs, and basically they're able to combine both into a separate model. And so the text encoder that this particular model uses is the clip text encoder, and the image embedder is the dense prediction transformers. So it pairs high capacity and text encoders to produce robust zero shot classifiers. So this is how, without using actually any training data, you're using pre-trained models, which one of the models, which is a text encoder, which embeds the text data, and the other one is a image encoder, which basically embeds the image. And both of these are transformed into are correlated by basically producing a tensor, and that tensor is able to give us an output by segmenting the data into separate regions. And yeah, and this is what we're going to be watching or learning about, or going more into a deep dive into the next slide. So the mechanism, this is the image which probably most of you are going to be familiar with. So this is the input image and the image encoder, which in this case is a dense prediction transformer, and the text encoder, which uses these input label sets. And the text encoder, of course, is the clip text encoder. And here you can see the yellow boxes is the correlated tensor. And this basically is the output, which is which is by H into W into N blocks. Now, before the final output, I forgot, I did not mention one thing, which was the spatial regularization blocks. So what do the spatial regularization blocks do? So what they want to do is essentially reduce the input image resolution and regularize the image, because you can get images of any sizes. You do not want your model to uh, depend, or you do not want the efficiency of your model to be dependent on the size of the input. So to regularize that, the spatial regularization box are inputted or put in before the last step, so that the output is always consistent. Of course, after the process is done, you can always upsample the predictions to the original input resolution, so the image does not come out as distorted or low resolution. So this is another example. This is a good example of the model in practice. So you can see, if your inputs is this image and the two text encoders, which is other and dog, so it only uses other and dog. So the dog is classified as red and other is all classified as black. Similarly, as you keep adding text inputs, the model is able to segment the image into different areas. You can see the similar for this mountain bikes and people image, and this wall, chair and other image. So you can see how well LSEG is able to produce an output with semantic image segmentation. So one of the novel things about this model is that it enables the synthesis of zero shot semantic segmentation models on the fly. Is there a problem? Oh, okay. No. Yeah. So basically, what that means is the user can input, resize, shrink, and expand the label set of any image at any time. And you can see, as mentioned in the previous images, that LSEG is able to output different segmentation maps based on the provided label set. So even if you provide the same image over and over, because because of different text inputs every time, the segmentation will always be different. And that essentially signifies how strong the LSEG model is, because it's not just relying on it's not just relying on the labeled instances, such as which few shot and one shot approaches use. It is able to use the text embeddings from the clip model and the image embeddings from the dense prediction transformers, and basically convert that into an output which performs this segmentation on the fly. And one more experiment or the training details which is notable, or which is to be noted, is that during the final step of the spatial regularization, there are two different inputs. One is the inputs from the text encoder, and one is the inputs from the image encoder. Both of these should not be interacting with each other at any time, because these are separate entities, and if they interact, it's essentially as you're letting your model learn the uh, learn the test data. You're giving your model access to the test data before final prediction, which is something that does not work. And obviously this was fixed by using two functions, which was one of which was the nonlinear activation depth-wise block, and max pooling operation using the bottleneck block. Now we talk about the performance and the comparison with other models. So before I talk about this, there are two things I want to two things or three things that are three data sets essentially, which I want to talk about. So you can see that the backbone or the model comparison, but you also have to know that there are three different data sets upon which this model was built, which was the COCO dataset, the Pascal dataset, and the FSS dataset. So the COCO and Pascal dataset are very well labeled, and they have 20 different classes with 4 folds each. But the FSS dataset, on the other hand, it claims to have 1,000 object classes, but it has a significant number of unseen and unannotated objects. Now, moving on to the performance, you can see depending on the model and the backbone, and obviously the method, you can see in different I'll have to zoom in, I guess, a little bit. Nope, that's not it. mm, yeah. Let me just enlarge it for a second then. Oops. There we go. I'm sorry about this. I'm not really familiar with Google Docs much, but so essentially, you can see what are you looking at. If you don't understand what you're looking at, just look at these two columns on the right side. If you see these two columns, you basically able to understand. So what is IOU and mean? So mean IOU and FB IOU, uh, these are segmentation evaluation metrics. So like you have precision and recall. For image segmentation, mean IOU and FB IOU are the segmentation metrics. As you can see, you can think that, oh wow, but HSNet with the ResNet 101 backbone is performing better than LSEG. But the thing is, you have to notice the fact that it is a method which is using one shot. Whenever you're in taking one shot, you already have to consider the fact that you are taking a lot of inputs, you're taking a lot of computation power, you're taking a lot of manpower, which is going to be used in using and in annotating and basically labeling that data. However, when you compare it to other zero shot models, you can see that LSEG with the VIT L16 approach, in the zero shot approach, is producing the best results. So yeah, and you can see similar things in the COCO 2020 dataset, that in the zero shot approach, it is by far performing the best compared to ZS3net, which was the previous best model. And next we move on to a few ablation studies. So yeah, this is the ablation study which derived the fact that the best text encoder that was found was derived using the ResNet 50 by 16 model. You can see that the pixel accuracy within that is 80.26%, and the mean IOU is 40.36%. And you might think, why is the mean IOU so less? Well, this is just the text encoder. The image encoder has not been inputted yet, so that's why the MIU is so little. And also within these, you can see the highest improvement compared to the previous depth is using the two bottlenecks blocks. And you can see, compared to every other metric, this is probably the best metric. And so this is what I mentioned earlier. The RN 50 by 16 achieves the best performance among all text encoders and surpasses the weakest ones by 2.5%. And yeah, and this is the classic image, or this is the classic image that you might all be familiar with how with each step, if you add more segmentation labels, the image will be segmented into more parts. And yeah, so that's basically an overview of LSEG. I know I probably wasn't the best explainer, but the thing is, I myself have only a higher level overview, and there's a lot of technicality and stuff within the model itself, which I encourage you all to explore. But if not that, if you just go to the GitHub, I'm pretty sure you all have the link. There's a simple way to implement the demo and see how it works just by using Jupyter Notebook. You just have to create a folder and then just deploy the lsec.demo.ipnb, and you'll be good to go. So yeah, that's it. If you guys have any questions, me, Elliot, and Georgios will be answering them now.
Why don't you use like the accuracy in the classification of the classes? Why do you choose like IU, which is intersection over union?
Intersection over union